Okay, so we're going to begin our discussion about how elements interact with one another and how they form compounds. I wanted to start off with this, with a video concentrating on the periodic table. Now I have this periodic table open from ptable.com, the dynamic periodic table. I've recommended this to all of y'all before, but this is a really useful interactive website. It lets you actually select the features that you're interested in about your particular element. So you can actually use this to look at different properties. You can actually, well, I really encourage you to go play with this table, but I'm going to call your attention to the orbitals right now because that's something that we've actually looked at before. We didn't use the word orbitals, we used subshells to describe these, but these also can be described as orbitals. We have s orbitals, p orbitals, d orbitals, and then f orbitals are actually down here in the lanthanides. So we can also click on one of these atoms, and I'd like to use this as an opportunity to sort of show you how we stacked up the electrons. That's going to be very important discussing the way that these different atoms on the periodic table communicate with each other. Let's look at these behaviors. First of all, when we go to hydrogen, you can see here at the in this area, there's you can see the boxes, and I told you that we have these little arrows that we sometimes write that indicate that there's an electron there, right? If we move to helium, then you can see that another arrow pops in there, so you can see the 1s shell or subshell is entirely filled for helium in the ground state. We can go to lithium, and that adds another electron, and you can see them stack up in the way that we talked about in the previous information. So beryllium, on to boron, you get that fifth one. Now notice what's happening. Notice what's happening here is we've moved from our s shells to the 2p shell, right? And then when we move to carbon, it starts to fill these up one at a time. We get to oxygen, it starts to fill them up like this. Fluorine, almost full, and then when we get to neon, then we've entirely filled up our S subshells and our P subshells. Remember we talked about valence electrons, and this really gives you a notion for what those valence electrons are. So here we have essentially, we have boron here would have one valence electron, right? So that valency is really about unpaired electrons, electrons that are available there to interact with other atoms. So we're going to look at how that, the basic mechanics behind how two atoms are going to interact with each other. And I want you to think in terms of this. So if you will, while the video is running, please pull up this ptable.com and see if you can play around with these while we're messing with the video. So follow along using the periodic table here as we discuss these things on the drawing pad. Okay, let's begin talking about how we're going to take these elements and anticipate the way that they're going to join with each other and understand why. So I'll mention to you previously that there are basically two things that an atom wants to do. Let's keep those labeled up here at the top. The number one thing that an atom wants to do is to fill S and P subshells. Or now we know a new term, orbitals, right? So the S and P orbitals or subshells, either one, that you want to use, either word you want to use. Those atoms love filling those up, right? So that's our number one priority, and number two priority is they like to be neutral. Okay, meaning that if you have a positive ion, in other words, if your atom has no longer considered a neutral atom, but it's positive instead, then it's going to be attracted to negative things. And if it's negative, then it's going to be attracted to positive things. So, or we can write that as neutrality, okay? So these two things describe the majority of what's going on, vast majority of what's going on in chemistry. So let's go ahead and start taking some atoms and then asking ourselves what's going to happen between those atoms. So the first thing that we could do is look at, let's say, an oxygen atom, and it's given as O. So that's not actually a ball, that's actually the letter O, right? And let's say hydrogen atoms, okay? So why don't we take a look at what the structures look like around these things. Now we have a periodic table that I'm keeping in the background here, so if we ever need it, we can pull it up. We can see immediately, we know hydrogen already. We know that one. That one has one electron, right? So we know that it has one proton and one electron. So I'm going to go ahead and I'm going to put an orbit around this thing. Okay. Let me make that gray. Okay. And then we're going to place an electron on that. So it has one electron, right? Let me make that a regular dot. So one electron. And now we can look at the electron structure for oxygen. So if you look at the oxygen here, it is 8, and so this is a frozen picture, so it's frozen on sulfur here. So we would need to fill these up on our own. We would need to say, okay, I am going to I'm going to fill up this one. I'm going to fill up this one. I'm going to fill up some of these. Now we've already actually done some of this filling up. So we've already done some of this filling up, but in the previous videos that we did for last week, but we are going to go through them again because it doesn't hurt to get a second, a second coating of information, right? So remember that oxygen has 8 protons and 8 electrons. Let's go ahead while we're at it and label our protons as well. So hydrogen has 1 proton down here. Oxygen has 8 protons. So I'm going to, let's put it, it's 1, 2, 3, 4, 5, 6, 7, 8 protons here that are bound into the thing. And now when we make our orbitals, we'll have our S, n equals 1, our n equals 2, and we'll have our n equals 3. You can keep going with that, right? We're not going to need the n equals 3. So what we'll do is we'll kind of compartmentalize this into S and P so that we have the n equals 1, and then there's the S subshell, and then the n equals 2, and on that one we're going to have both S and P. So you can see that here. If you just go along with the periodic table here, we have in the n equals 1 we have an S shell, right? And in the n equals 2 we have an S shell and a P shell, right? So we're not going to make it farther than that. We could keep counting upward, but with oxygen we're not going to count further than that. If you run into sulfur, obviously you do, so we'd have to, or aluminum or something like that. So we're going to count up to oxygen, and we're going to say we have 8 protons in here, so therefore we have 8 electrons. Let's go ahead and count up our electrons. We have 1, 2 in the first orbital. And then when we go up to the 2s, we have 2 and the 2s. So I'm going to actually kind of cut that off there. And then all the rest of them are going to be in the p orbital. Now, previously I gave you 2 rings for that, but I don't want to confuse that with the n equals 1, n equals 2, n equals 3. So I'm just going to kind of cram all those onto the same ring here. So now we have 1, 2, 3. How many more do we need to go? 4. Now we actually have spots for the 5th and 6th that are not going to be filled. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. Let's count those up here. We have 2 in the 1s, 2 in the 2s, and then we're going to have, let's count those. I'm going to count those in a bigger way up here so that you can see what I'm talking about. So we have, for our oxygen, here is 1s, 2s, 3s, and then notice in between, we have this. So let's count those up for our oxygen. We have 1, 2, 3, 4, 5, 6, 7, 8. So what that does is it leaves 2 seats open for more electrons. Now, what is our number 1 priority here? Our number 1 priority is to fill up the S and P shells, okay? So we're going to basically have a bargain occur between an oxygen atom and a hydrogen atom, because both of these want to fill up their shells. Look at this. The hydrogen also has a shell over here that needs to be filled up, right? So it has a vacancy as well. Well, what are we going to do about that? We're going to, maybe, what if we had another hydrogen? Okay, so with this new hydrogen, I now have an oxygen that has 2 vacancies, and a hydrogen that has a vacancy, and another hydrogen that has a vacancy. So what we could do is we could say, hey, what if I could use, my oxygen is going to borrow that electron every once in a while, and borrow this electron every once in a while. And the hydrogen is like, I'll tell you what, why don't I borrow this electron every once in a while and borrow this electron every once in a while. So I want you to think about this in terms of like, so you could think about this in terms of like custody. Like, so in other words, the oxygen is like, hey, I've got my, I've got all these kids, and I'm going to let them go stay the weekend over at the hydrogen. And the hydrogen's like, well, yeah, I'm going to let you guys stay over at the oxygen. So that way, the oxygen always feels like it actually has 8 on the outer ring, and the hydrogens always feel like they have 2 on the outer ring. So let me give a different example that will kind of highlight this kind of bonding. But first, let's label this kind of bonding. Again, I hesitate to use this label for this bonding because hydrogen atoms are a little bit different. But the whole idea is covalent bonding, okay? Again, this is hydrogen, so it's not exactly a covalent, but it gives you kind of a sense. Let's do a better example. Let's take the concept of 2 nitrogen atoms. So I have a nitrogen atom, and let's build up our ground state for our nitrogen atom. First thing we do is we look at how many protons the thing has. It has 7 protons. 1, 2, 3, 4, 5, 6, 7 protons. And then, and remember, those are stuck down in the middle, right? When I build my shells, I'm going to say, let's see, I got my N equals 1 shell, my N equals 2 shell. I could keep going, but again, I'm not really going to need that. And I can also kind of partition this off so that we can keep like 2 spots for the S and 6 spots for the P. And if so, the blue is going to be here's the N equals 1 S shell, and here's the N equals 2 S shell, and the greens are going to be for the N equals 2 P subshell. Okay, so let's go ahead and place our electrons. We have for nitrogen. Let's go ahead and look at our orbital boxes again. There's 1s and 2s, and then there was a 2p that was right in between the two. Right? Oops, that's not. It's up here. Sorry. Better than that. There's also a 3p up here, but we're never going to get there. Okay. Let's fill these up. We have our how many electrons? Well, if we have 7 protons, and this thing was basically born with 7 electrons, and so we get 1, 2, and that one's filled. And then we get 3, 4, and that's filled, so that's 4. And then we get 5, 6, 7, and then there are some spots. And that's it. Okay. Now, now that we've established what the ground state of nitrogen is, we've also established that there are 3 holes, 3 things that are preventing this thing from being entirely filled. We love having either filled or empty subshells, prefer filled. So how are we going to fill this up? Well, what if we duplicated this thing so that we had 2 nitrogens? Okay, so let's fill up our electrons here. We've got 1, 2, 3, 4, and then we got 5, 6, 7, and then this one, same thing. 1, 2, 3, 4, and I'll go 5, 6, 7. Okay, and so what we can do is say, I'll tell you what, this other atom here is going to pull that same sort of custodial arrangement so that sometimes it donates this electron there. And sometimes, but it doesn't really donate it. All it does is kind of let it borrow it. If it donated it, it would be like, here, you can have it forever. And that is not what happens in this case. So it would be better to kind of have our arrows drawn in between both of them. So, as you can see here, these share electrons, these share electrons, these share electrons, and these share electrons. So that essentially, and that's a lot of arrows here. So basically, I'm going to get rid of those, but I want you to kind of get a sense of each of these empty boxes has a corresponding box over here that's an electron that kind of shares with it. Now, that's a little bit hard to imagine, but if we imagined it like this, where we have our nitrogen atom here and another nitrogen atom here, and then you've got all these electrons that are just buzzing around, right? So they're going to look something like this. We're just buzzing around like these. Then what's going to occur here is that sometimes this electron that's in this particular orbital is going to kind of be like, oh, I'll spend some time over here and make this atom happy. And then this one that's over here is like, oh, I'll spend some time over here and make this one happy. And then this one is like, oh, I'll spend some time over here and make this one happy, right? And so we end up with these 3 bonds of basically shared electrons. I'd like to add to the word covalent and say that it's essentially shared electrons. But sharing electrons didn't necessarily make sense unless we understood why they are sharing the electrons. And the principle here is that we do not want to have empty spots in our orbitals. And so if we share electrons, then both of us can be happy. Okay, so this is the idea behind covalent bonding. Essentially, we are counting up all of the electrons that are on the outside and trying to fill up our S and P shells until they create sort of a puzzle of pieces that are all happy. Okay, this is covalent bonding. Now let's move on to another type of bonding. This other type of bonding is called ionic bonding. I'll give you some hints about which one you would expect in any given circumstance. And it turns out that most of bonds are really a little bit kind of fuzzy. They're like, I'm kind of ionic, but I'm also kind of covalent. But you'll get a sense of this as we look at this. A really great example of that would be sodium. So let's take a sodium atom, okay, and figure out how many electrons it has. And let's take a chlorine atom and figure out how many electrons it has. All right, so the first thing we're going to do is count all the protons. Now, I'm not going to make that many dots, so instead I'm just going to say 11 protons and 17 protons, okay? That means we need to count up all the electrons, right? Let's get our orbitals together. This time we're going to need a few more. Here. Oops. Okay, so 1, 2, 3. 1, 2, 3. Oh, I'm doing that on purpose. Okay, let's count all this up. If we were to count our electrons in sodium, we know that we have to count all the way up to 11. So let's do that. We're going to start off with our first 1s, and that takes 2 electrons. Now when we move up to n equals 2, remember we have an s and a p, so we're going to divide that up. So let's put the 2 of them in the 2s shell, and then we're going to keep going. We get 2p is going to be 1, 2, 3, oops, 1, 2, 3, 4, 5, 6, okay? So that means, so what do we have so far? We have 6 in here, we have 2 in here, and 2 in here. That's 10, right? Okay, so how many do we need? We need 11. Well, if we need 11, we need one more. Well, we don't have any more room in the n equals 2, so we're going to put 1 extra electron here in the n equals 3 shell, okay? All right, now, let's do chlorine. Same process. Actually, we can go all the way up to the same thing we did with sodium here. We know that we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10. We need to get all the way up to 17 electrons because we have 17 protons. So that means we need 7 more. So we're going to do, okay, let's divide this one up again into here's the 3s shell. So we've done 1s, we've done 2s, the 2p, and now we've started on 3s. We filled that up, and we still have more to go. We got 12. We need to keep going. We need 5 more, so we'll go into the now into the 3p shell. Okay. And so actually, if you carefully notice here, we could actually show that it looks exactly like this sulfur, except for it has 1 extra electron. So really what you could do is just put another electron in that little box and you would have it. So let's fill up our atom. We have 3s2, and then we move into the p. So we have 1, 2, 3, 4, 5. We're missing 1, right? almost filled. Almost. It would have been so pretty. Completely filled, except for one. It's like missing the last card in your baseball card deck. It's like missing the last coin in your coin collection, right? This chlorine atom really starts to eye this thing. It says, hey, are you going to eat that? And the sodium is like, well, no, I don't really need it that much. I've got all these filled shells, and then there's this extra one out here. And so then chlorine says, give it to me, right? And so it's immediate. It grabs this electron, it puts it in the box, right? And so we're gonna X this thing out. So, nope, this is no longer there. It goes over here now, and the chlorine is happy. The chlorine stole the electron. The sodium donated the electron. This is not borrowing. This is not sharing electrons. This is straight up theft. This chlorine took the electron. Why? Because the sodium was such a pushover here, right? In the case of our two nitrogen atoms, that wasn't the case at all. Those two nitrogen atoms were like, hey, we all both kind of want to hang on to our electrons, but in this case, nope, bullied into letting that electron go. So now we have a new feature. We now have, let's look at this carefully, we have a sodium atom, and our sodium atom, let's put these in boxes real quick. Our sodium atom has how many protons and how many electrons? It has 11 protons, right? And it has how many electrons? 10 electrons now. Why? Because one was stolen, right? Now let's take a look at our chlorine atom. The chlorine atom, oops. And the chlorine atom has 17 protons and how many electrons? 18 electrons. This means that we do not have atoms, we have ions, right? It means that if we count up the total charge, we get 11 positive and 10 negative, which means the sodium overall has a positive charge of 1, right? And the chlorine, if we add up all of our charge on that atom, is now an ion with a negative charge of 1. We call this one an anion. You can think of an as in you're about to say an negative ion, but anion, right? And then we have cation. And I know this is terrible, but it will help you remember what a cation is. My cat is really a punk, and so sometimes my dog gets really mad at the cat and just like wallops and knocks it right out, and so it just sits there like ugh on the floor, like just like knocked out for a little while. It doesn't actually, but it sure dreams that it does. Actually, the cat is completely unbothered by it. But see these little plus signs? Cation. All right. I know it's terrible, but now you're never, ever, ever going to forget it. So, oh, the power of morbid thinking. Okay, so we have a cation and an anion. If you have a positively charged ion and a negatively charged ion, what's going to happen? Well, positives and negatives don't like being positive or negative. That's our second rule. So they attract to one another to create an entirely neutral molecule. Okay. Now it just so happens that what they do here is they go, okay, they take a sodium ion here, and then a chlorine goes, hey, how's it going, neighbor? And then because this one is closer to the next sodium than this sodium is, then it says, hey, how's it going, chlorine? And then it's like, well, oops, That's totally positive over here. So another chlorine is like, hey guys, how's it going? And then another one's like, wait a second here, I see a negative. And then another chlorine is like, wait a second, there's two positives over here. So it starts to form a crystal of sodium chloride or table salt. So this is called ionic bonding. The main difference here is that in covalent bonding, the two atoms share an electron, and so it spends sort of most of its time sort of transferring between atoms. So a perfectly covalent bond would spend just as much time on one atom as it would on the other. Whereas an ionic bond has a permanent donation of an electron from one atom to the other, and then it's entirely electrostatic in bonding. So it's not the sharing of the electrons that causes the bonding to occur. It's actually just the fact that positive ions and negative ions are attracted to each other. And electrostatic bonding is quite strong, so this is actually not a weak bond at all. Okay, so this is the two primary types of bonding. There's one third type of bonding that is difficult to describe, so I'm not gonna describe it. If any of you is interested in it, I can describe it, but I don't want to overwhelm you in one video because this is already a lot to take in. We also have another type of bonding in these D-shell atoms, or these um, transition metals, called metallic bonding. Okay. Now, again, I said we have ionic bonding and we have covalent bonding, right? So covalent bonding, how do I know if my two atoms are going to exhibit covalent bonding versus ionic bonding? We did kind of give you a hint here because this electron was this puny extra electron. Each of these over here on this side, and again, hydrogen was a terrible example, but it's sort of an exception to all rules, so I used it to start the conversation. But all of these over here on this first column here have only one electron just on the outer shell, just like this sodium. Now, yes, they have different numbers of shells, but they all have the feature that they have one extra electron on there. So these are called the alkali metals, right? And then we have the alkaline earth metals in the second one, which have two electrons on the outside. Both of these columns have a tendency to form ions with these columns here. It's also totally possible you can get magnesium chloride or something along those lines, right? Or magnesium fluoride. So we'll talk a little bit more about that in our next video, where we talk about how many we would expect to form by looking at how many atoms we would expect to form in a molecule by looking simply at where they are on the periodic table. Okay.